So before we begin the session, I would like to make an announcement that just in case you see a request control button, please do not click. And if by chance someone clicks on it, the presenter, if he or she is popped up by such a message, please ignore that. And the closing ceremony link for tomorrow's session is there in the web information kit that you have received in your email. So please join us for the closing ceremony tomorrow. Now over to you, Professor Dhingra.
Thanks a lot. Welcome you all to this evening part of plenary session 3 on research in solar and planetary sciences. We have 10 presentations lined up, and I would encourage all the presenters to try to keep time, and it will be good if you can leave a few minutes to answer any questions. So with that, I'll give another 1 minute to start, and we can request the first speaker, Satvika Jaiswal, to please share her screen in the meanwhile. Okay, so just wait for a minute and then we can get started. So for the first set of speakers who are scheduled to talk for 20 minutes, I'll give you a warning at 17 minutes, so you are aware. So Satvika, we can start. This talk is on neon in terrestrial planets, and presenter is Satvika Jaiswal. Please go ahead.
Okay, my screen is visible?
Yes.
Okay, today I'll be talking on neon in terrestrial planets. The major objective is to identify the major trap component and to understand the differences and similarities of the terrestrial planets from noble gas isotopic perspective. So with the planet formation, Earth and other planets have a common origin and they originated at the same time from the same source. The most accepted theory for the formation of solar system is based upon the idea that our solar system originated from the gravitational collapse of rotating molecular cloud core made up of gas and dust. At the center, the sun formed and all the densest material filled in over time, it ignited, and this ignition blew the debris into a ring orbiting the sun. So our solar system consists of distinct types of celestial bodies, which include the sun, 8 planets, asteroids, dwarf planets, and these bodies form in the same protoplanetary disk that is made up of gas dust surrounding them. So the inner planet consists of Mercury, Venus, Earth, and Mars, and they are referred to as the terrestrial planets. And the outer 4 planets, Jupiter, Saturn, Uranus, and Neptune, they are known as the gas giants. And the main asteroid belt lies between Mars and Jupiter. The basic building blocks of terrestrial planets, like in the initial conditions of solar system formation, planets were originated when small dust and rock pieces aggregate into rocky planets by a process of accretion. But some of the objects never accreted, and they retain more information about the initial conditions of solar system. A considerable data indicates that chondrites, they are the meteoroids that originated from an undifferentiated parent body that formed within few million years of beginning of solar system. So chondrites are the basic building blocks of the terrestrial planets, and they are the major precursor material. As the terrestrial planets, they don't have the same precursor material. They may be same, but the proportionate may vary. As we have different models for Mars and Earth, also for Moon, but we don't have any knowledge for Venus and Mercury. So the terrestrial planets form from different proportionate of major precursor material. That tells us that the initial material and the degassing history may vary. Because of the presence of different proportionate of precursor material, Degassing history in a way. So these are the Mercury, Venus, Earth, Mars, Vesta, Moon. These are the rocky objects of the inner solar system. They all are differentiated. We don't have any bulk rock on Earth or greater than 1 giga in our age. There is thick atmosphere on Venus and Earth and a thin atmosphere on Mars, and there is no atmosphere on Mercury, Moon, and Vesta. The size of these parent bodies ranges from 500 kilometers to 12,000 kilometers. And all the rocky objects, they are differentiated in early time. We see the geological activity of the inner solar system object. We see that Earth and Venus, they are still active and evolving. In case of Mars, the activity stopped 150 million years ago. And in case of Moon, Mercury, and Vesta, there is no geologic activity after 4 billion years. How planets evolve with time? There may be changes in the interior, changes in the surface, as well as changes in the atmosphere. So the changes in the interior is due to the differentiation or the volcanism. Changes in the surface is due to the geological activity, or there may be large or small impacts. And changes in the atmosphere is due to the various factors like gas deposition by IDPs, erosion driven by the solar radiation, and many more. The noble gases. Why we are working with noble gases? The stable noble gases, helium, neon, argon, krypton, and xenon, they provide a unique tool for planetary research. As they are inert, they didn't show any chemical reaction, they are highly volatile in nature, and they are rare, very low abundance in rock. So the key to understand the history of volatile degassing from interior of planetary bodies and to constrain the type of precursor material information regarding our Earth and solar system, noble gases plays a key role. So the 5 stable noble gases comprises a total of 23 stable isotopes. However, much of the utility of noble gases is based on the widespread variation in their isotopic composition. Asteroids. Asteroids are basically the minor rocky objects in our solar system. And these asteroids, the diameter of these bodies ranges from several meters to hundreds of kilometers. And most of the rocky asteroids, they orbit between Mars and Jupiter. We have 2 major asteroids, one Ceres, which is a undifferentiated asteroid, and 4 Vesta, which is a differentiated asteroid. So we are starting here the 4 Vesta, which is a differentiated asteroid. The asteroid Vesta is the largest differentiated asteroid in the main asteroid belt and is the only asteroid which remains intact in the solar system, which was differentiated into basaltic crust, ultramafic mantle, and metallic core. The small size of Vesta, with a mean diameter of approximately 525 km, it mirrored the behavior of other differentiated planets. HEDs, that is Howardite, Euclides, and Dagenites, have been long recognized as representing a related group of meteoroids and therefore together referred to as the HED clan. Our understanding of Vesta HED link has improved as after the NASA's Dawn mission has completed orbiting Vesta for more than a year. The spectral characteristic of Vesta clearly matches with the HED meteoroids. The HEDs are the largest group of achondrite meteoroids, which are basically mafic and ultramafic igneous rock. They are diagenites, they are orthopyroxene rich, they may contain olivine, like with or without olivine. They are coarse grained, they are monomic cumulates, and they are likely represent the lower crust or mantle of Vesta. Euclides, they are the most differentiated member of HED clan, and they are mafic rocks. They consist mainly of pyroxenes and plagioclase. They are likely derived from the crust of Vesta. And the Howardites, they are described as the regolith breccia that are formed by the impact-induced mixing on the surface. They are basically the polymic breccias. And they have material from both the euclides and diagenites, and they likely derive the surface of the parent body, surface of the Vesta. This is the neon 3 isotope plot of 20 by 22 versus 21 by 22. The noble gas isotopic feature that is observed in the meteoritic material, they are results of various processes that have occurred over a long span of time. So the greatest differences between the solar system object can be seen through the neon 3 isotope plot. In this plot, we have represent the solar wind component, phase Q, air for the Earth's atmosphere, HL for the planetary component, SCR here is for the solar cosmic ray, and GCR is for the galactic cosmic ray. Next figure, it shows in this figure the neon isotope ratios for the mantle rocks. They are typically displayed on the neon isotope plot. In this figure, the MOB and OIB indicates the solar light trap neon. And the mixing line for MOB, they extend to greater value of 20 by 22 than the mixing line for OIB, that is indicating more 21 neon enrolled in the MOLB than as compared to OIB. From this plot, it is also seen that the interior is solar type and the interior component is different from the atmospheric component. Next, we have plotted all the stepwise data for eukaryotes. So in this neon 3 isotope plot of 20 by 22 versus 21 by 22, we have plotted for the individual step of neon isotopic data of eukaryotes. And from this plot, it is clearly seen that there is no such elevation in the neon. So there is no solar wind component in the same, and majority of data lies in the spatial range, and also they are dominated by the GCR, that is the galactic cosmic ray. So from this stepwise analysis, it is clear that the majority of data lies near the GCR range. Next, with the single step method, we have plotted all the eukaryote data, and from this we also seen that the majority of data lies near GCR. So it may be due to the degassing of parent body, and it is a lighter gas and it can quickly escape. So we are not getting here the trap component. After this, we have plotted for the diagenites. So we have plotted all the diagenite data, and with this we see that as we have few samples and all the samples lies near the GCR range. So with this we cannot pinpoint the isotopic ratio, that is still needed to be done. For this we say that we require those samples that are free from the GCR. Then with this, after this we have compared our data with the other terrestrial planets. So we have plotted the Mars atmosphere, Venus atmosphere, Earth's atmosphere. This region represents for the eukaryotes and diagenites, and with this we see that eukaryotes and diagenites represent a region near GCR, and also we see that the Earth's atmosphere, Mars atmosphere, and Venus atmosphere, there is a distinct isotopic composition in these three parent bodies. And we also seen the interior component where we have plotted MOB and OIB representing the Earth interior and Jessica representing Mars interior. Also these, with this also we have seen that the isotopic ratios of the interior component of these planetary bodies, like for Earth and Mars, is also distinct. So with this we say that with the neon isotopic ratios, the isotopic ratios of atmosphere also differ from the interior. Now we compare the neon isotopic abundance of neon isotopic trap neon in different reservoirs. So we say that the 20 neon concentration in eukaryotes and diagenites is depleted when we compared it with the carbonaceous chondrite. And also when we compare the abundance of 20 neon with Earth, like from MOB and OIB and Chessigini, it is also varied. So the abundance of Earth, Mars and Vesta also differs, and abundance of noble gases are also depleted in eukaryotes and diagenites when we compared it with the carbonaceous chondrites. After this, we compare the neon isotopic ratios with other noble gases, whether we to see whether we observe the same trend as neon. So this table shows the 20 neon, 36 argon, 84 krypton, and 132 xenon trap values or abundance in carbonaceous chondrite, Jessica, MOB, and OIB. As carbonaceous chondrites, they are enriched in noble gases. So we took as an example that is the major noble gases are derived from the carbonaceous chondrites. So the abundance of neon, argon, krypton, and xenon is very low from the mantle of Earth and Mars when we compared it with the carbonaceous chondrite. And similarly, it like this ratio will be same with the enstatite or ordinary chondrites. So abundance is low with respect to carbonaceous chondrites, and also the abundance of both Earth and Mars also varies. As we don't have like lunar samples and lunar meteoroids, they are full of solar wind gases, so it is not easy to deconvolute the interior gases. And we don't have any rock samples for Mercury and Venus. In the next table, we have also plotted for the, we have also added the data for eukaryotes and diagenites. And with this data, we also say that the abundance of noble gases, they are depleted in eukaryotes and diagenites, like in 20 neon, 36 argon, 84 krypton, and 132 xenon. They are depleted when we compare it with the carbonaceous chondrite, and also the abundance of this noble gases, they differ in Earth, Mars, and Vesta. Next is the elemental plot, where we have showed that 36 argon by 132 xenon versus 84 krypton by 132 xenon. This first plot is for the differentiated object, where we have plotted Jezegini for Mars, eukaryotes and diagenites representing Vesta, and Mob and OIB representing Earth. So the elemental ratios in interior of these objects is quite different, and from figure it is clear that eukaryotes and diagenites that represent crust and mantle of parent body, and they are also representing two different components. Since they are formed by various mechanisms, because of that there is a loss of gas depending upon the activity that is taking place on that parent body. So the elemental ratios of these three planetary bodies is different. So distinct elemental ratios, they suggest a different degassing history of the differentiated parent bodies. Then we also in the second plot we have added the carbonaceous chondrite, Q, and solar wind component. So we see that there is a two different trend lines for the differentiated and undifferentiated object. So, so the extent of degassing, differentiation, these all play together, and they gives us the present ratios. So with this, noble gases are very useful for comparative planetology. Neon in mantle of Earth, Mars, and asteroid Vesta is depleted with respect to chondrites, and also with the heavy noble gases. There is a variation in abundance of neon, which is imprint of the different geological evolution, and the elemental ratios of noble gases are also distinct in interior of differentiated objects. And with this, we are proposing, based on the study, that there is no direct samples on Venus, Mercury, and Moon, and hence based on the above study, we propose that there could be a distinct component and different degassing history in the remaining terrestrial object. Thank you.
Thank you very much, Satvika, for maintaining the time. We have enough time for questions. I see a question in the chat box. Avad Kumar is asking, in the 3 neon isotopic plot, why most of the meteorites lie near the GCR region? Did you get the question, Satvika?
Yeah.
Okay, go ahead.
Most of the, most of the, with our data also, it clearly suggests that most of the data points lie near the GCR region.
Yeah, the question is why. Go ahead. Please go ahead, Satvika.
Yes, sir. Wait a minute.
Okay. And meanwhile, if there are any further questions, you can type them in the chat box or raise your hand. If you would like to take it up later, that is perfectly fine. You can type your answer in the chat box.
Okay.
Okay. Are there any other questions? Okay, I don't see any. Thank you very much, Satvika, for your talk. So we move on to our next speaker, which is Sana Ahmed from Physical Research Laboratory. The title of her talk is Gas Phase Modeling of the Cometary Coma of the Interstellar Comet 2I Borisov. So Sana, you may start.
Yes, am I audible?
Yeah, and your slides are visible. You can go ahead.
Thank you. I'm working at PRL with Dr. Kingshuk Acharya, and today I'm going to be talking about my work on the modeling of the coma with special reference to the interstellar comet 2I Borisov. To begin with, so comets, they are numerous objects of the solar system, and they are made up of refractory dust grains and also volatile species. That flows very early during the solar system formation. And in general, if we look at a schematic of the protoplanetary disk, then the outer regions of the protoplanetary disk, where the temperatures are low, that is generally considered as the comet forming region. Now, since the volatiles froze very early, they and did not undergo much alteration after the formation, after solar system formation. So they do preserve some amount of signature of the primordial disk composition, and hence they can the study of comets can really tell us about the composition that existed at the time of formation of the solar system. When a comet enters the inner solar system, basically it has a nucleus which contains all the frozen volatiles. And in the inner solar system, due to the solar heating, the volatiles are going to sublimate from the nucleus, and then they form the cometary atmosphere or the coma. And the atmosphere can sometimes extend to form the tails. Since the albedo of the nucleus is very low, so when a comet is remotely observed from ground-based or space-based observatories, then in general, our knowledge about the nucleus comes indirectly by studying the coma. So the typical composition of the coma, it primarily consists of water. About 70 to 80% is water. This is followed by other volatile gases like carbon monoxide, carbon dioxide, ammonia, formaldehyde, methanol, and so on. And these species that are sublimating directly from the nucleus, they are called the parent species. And at present, the total number of species, parent species detected stands at about 80. On the right-hand side is a plot of the abundance, range of abundances that has been observed of these parent volatile species. So the green bars, they indicate the range of abundance, and the numbers on the right-hand side, they indicate that how many comets these species have been detected in. The abundances of the other volatiles apart from water, they are given as percentage with respect to water. So the interstellar comet 2I Borisov, it was the first comet to have been detected in the solar system. This was discovered in August 2019, and orbital calculations firmly established this as having origins outside the solar system. And what really set this comet apart from the solar system comets was the high CO by H2O ratio. And such a high CO by H2O ratio has not been observed in comets at a heliocentric distance less than 2.5 AU. So this is a plot of some of the volatiles that have been detected in the interstellar comet. On the x-axis is the time relative to perihelion. That is, the negative numbers show the days before perihelion. Positive numbers indicate how many days after perihelion. And on the y-axis is the production rate. That is the number of molecules of a particular species sublimating per second. So we see that H2O and CO from this plot, they show nearly similar abundances. So we aim to study that what effect this high CO by H2O ratio is going to have on the coma chemistry and dynamics. So we used a gas phase model for studying the coma. We constructed the model as such, so we assumed that a comet nucleus is made up of certain frozen ices, that is the parent species. Now these ices, they are going to sublimate from the nucleus, and because of the solar UV radiation, they are going to undergo photochemical reactions, and they are going to form secondary species, ions, radicals, and electrons. And all of these ions, radicals, and electrons, they are going to react with each other and with the parent species to form even newer species. So a very active gas phase chemistry occurs in the coma. And this gas phase coma, we assume that it flows as a fluid. And we divide the fluid into three categories: the neutrals, the ions, and the electrons. So basically, from chemical reactions, what happens is that the energy that is released due to chemical reactions, that is not necessarily distributed uniformly amongst all the products of the chemical reaction. And that is why we have to make this distinction between the neutrals, ions, and the electrons. There is also energy exchange between these three fluids due to elastic collisions and inelastic collisions, and we also consider radiative losses. So then we apply the principles of conservation of mass, momentum, and energy, and we use these model equations, these three differential equations that are first order differential equations. And by solving these equations by numerical integration, we can find the properties of the coma, such as temperature, velocity, number density, the rates of the chemical reactions, the energy, the amount of energy that is exchanged between the fluids, and so on. So at present, our present model, it has nearly 400 chemical species that are connected by about 4,500 reactions. So the input conditions that we used for the model, we used the composition of the 2I coma composition of 2I Borisov, nearly equal abundances of H2O and CO, and some of the other volatiles, the abundances are given here. And we also ran the model for an average solar system comet, which is rich in H2O, that is about 86% H2O, and CO abundance is much lesser. So what we get is, after integrating the fluid equations, we have got the temperature profile, and the temperature profile is basically the variation of the temperature with cometocentric distance. So on the x-axis is the cometocentric distance, and on the y-axis is the temperature. So N, E, and I, they denote the temperatures of the neutral, electron, and ion fluids respectively. And on the left, we have for the comet 2I Borisov, and the right-hand side is the H2O rich comet. So qualitatively, we see that the temperature profiles are similar, but we do see some quantitative differences. Particularly, if we look at the neutral and electron temperatures, they are there is some amount of coupling that exists between them, because when the electrons are created, they undergo collisions with the neutral atoms, exciting the neutral atoms to the higher rotational and vibrational levels. And in the inner region where the density is high, so such collisions are effective. And when the frequency of such collisions reduces, then the temperature decouples. Now, in the water-rich case, since water has a much higher collision cross-section than carbon monoxide, that is why the coupling exists up to a larger distance. And the reason we need to calculate these temperatures is because the rates of some of the chemical reactions are very highly dependent on temperature. So the rates of the different reactions, they are going to be different in the different regions of the coma as determined by the temperature profile. Next, we come to the ion chemistry in the gas phase coma. So two very important classes of reactions are photoionization, where any neutral parent molecule, it changes into the ion form due to the gamma radiation. And the second is the proton transfer, that is any parent molecule, it is going to absorb a hydrogen ion and form the AH plus form, that is the protonated form. So in this schematic, like we see, if we have a water molecule, Because of photoionization, it will form H2O plus, and due to proton transfer, it will form H3O plus. And CO will form CO plus due to photoionization, HCO plus by proton transfer, and so on for the other neutral species. So in general, in an H2O rich coma, in an H2O rich solar system comet, we see a high abundance of the H2O plus and H3O plus ions because of the presence of a large amount of water. But in the interstellar comet, we see that the abundance of these two ions, that is CO plus and HCO plus ions, are also quite high because of the presence of a large amount of CO. And some of the other ions, the flux profiles are shown in these two plots. This one shows the nitrogen-bearing ions, and this plot shows some of the large organic ions. And if we look at some of the pathways by which the CO plus and HCO plus ions are formed, so as I mentioned before, CO plus is mainly formed by photoionization. This is denoted by the blue solid line. And some of the pathways by which it is destroyed is denoted by these dashed lines. So basically, it undergoes charge transfer reaction with some of the neutral molecules. And HCO plus again is formed by a proton transfer from H2O plus to CO, and also by ion neutral reaction between H2O and CO plus. So indirectly, we see that the more amount of CO we have, the more amount of CO plus and HCO plus is going to be formed. And the large amount of CO plus is also going to affect the creation of the other larger organic ions and neutrals. So in this plot, the solid lines, they denote the organic ions flux profiles for comet 2I Borisov, and the dashed lines indicate for the solar system H2 rich solar system comet. So we see that for all of these organic ions, the solid lines, they always show higher abundance, and that is because HCO plus ion, it is going to undergo proton transfer reactions with alcohol, and it is going to form the CH3OH2 plus ion, that is the protonated form. And then this in turn reacts with the other neutrals and the ions to form these other species. Again, H2COH plus is formed when a proton transfer takes place to the formaldehyde, and all these other species are in turn formed. To summarize, we see that the presence of a large amount of CO will affect the chemistry and the dynamics of the coma of comet 2I Borisov, and CO plus and HCO plus abundances are high because of the presence of a large amount of CO, and the presence of these two ions will cause an enhanced abundance of the organic ions and neutrals as compared to solar system comets. And what this means going forward is that studies are already underway to correlate the compositions of the solar system comets to the protoplanetary disk, and a comparative study of the interstellar comet with solar system comets will help in making a chemical inventory of 2I Borisov's natal disk. Thank you.
Okay, thank you very much, Sana, and thanks for keeping the time. We actually have a lot of time to ask questions, so if people have any questions to ask, you can raise your hand or put a message in the chat box. I don't see any questions in the chat box right now. So I'll just get started. Very nice talk. So it's more of an informational question. Did you develop the numerical model, or are you sourcing it from somewhere?
No, I developed it.
Okay. So the question is that, you are aware that quite a few missions have been sent to comets where we have some amount of in situ information, right?
Yes, yes.
So from a modeling perspective, have you thought of validating your model against such measurements? Because we can see all the different trends based on, first order reactions, and any model has a lot of assumptions. So how do you really validate your observations?
Gas phase coma chemistry has been done previously also. So we have benchmarked a model with the previous model results, and also we have made some comparisons with observations. Like we have the ion density profiles that we are getting. We compared it with observations for some other comets, and we saw that okay, it is matching what has been observed. So basically, since we are doing gas phase, we are doing the gas phase coma chemistry. So we rely on the ground-based and spectroscopic observations mainly for benchmarking and also for finding the coma chemistry. So
Okay.
in situ measurements as such, we have not used. We have used the spectroscopic measurements for benchmarking.
Okay. So just a small, follow-up to that.
Yes.
Is that when you are looking at these different species, you mentioned that this interstellar comet has high CO to H2O. So is that a problem in terms of benchmarking for this particular aspect? Do you have enough data to basically track down all the reactions in a high CO environment?
Yeah, we do have, yes.
Okay. Okay, that's from my side. I still don't see any hands up. Because we still have 6 minutes remaining, so I would encourage people to ask any questions to Sana, or if there are any questions for the previous speaker, Satvika. Are there any questions? You can raise your hand, or you can type in the chat box. I don't see any questions, so I will ask one question to Satvika as well. So in your presentation, Satvika, when you were showing the plot for different planetary bodies, I think you plotted Venus atmosphere having a significant solar wind component, right? Is that right? And I guess Satvika will need to be given the audio access.
Yes, sir.
Did I get it right that Venus atmosphere was having significant solar wind component?
Yes, sir.
So what can we infer from that? Like, what does that mean in terms of the, evolution of Venus? Because Earth and Venus are kind of compared as sisters. So can we get something from this particular information that Venus atmosphere has significant solar wind component in terms of the neon isotopes? It's perfectly fine if you want to come to it later. I just had these questions, so I thought uh, I'll just ask because we still have 4 more minutes to go.
Sir, I've just compared Venus. I have not worked much on Venus. I've
Okay.
just compared the isotopic ratios with Venus. Like we don't have. We are just working on the interior component. For Venus, we don't have any interior component. For that, we just compare the atmospheric isotopic compositions.
Yeah, but the gases are also coming from the interior, isn't it? Since
Yeah.
the planet is evolving, that gases are going to come out and be part of the atmosphere if it has enough gravity. Okay, I was just curious. And the other question was, this is a much simpler question. It's more of a amateur question, but it's always good to know things. So in your abundance plots for all the noble gases, neon, argon, krypton, xenon, I noticed that it seemed to be dependent on the mass. So higher the mass, higher is the abundance. Like heavier the gas, difficult. It is more difficult for it to be lost.
Escape.
Did I
Yes,
understand
sir.
it correctly?
Yes, sir. Exactly,
That
sir.
neon had a very low abundance, and xenon in general had high abundance for all the different samples that you analyzed.
Yes, sir. But in principle, the lighter gas quickly escape.
Mm-hmm. So, are there any other controls for the relative proportions of these gases
Yes,
apart
sir.
from the mass?
Apart from Mars, like there are different processes in the different parent bodies. Like the gassing history may differ. And
Mm-hmm.
like when we compare it with the parent body Vesta, where there is no atmosphere, so
Mm-hmm.
anything that is escape to space. So there are
Okay.
various factors.
So this proportionally higher abundance for heavier noble gases may not be seen in all cases, right?
Yes, sir.
Okay. Thank you, Satvika.
Okay, thank you, sir.
So I will introduce the next speaker. We have K. Channa Reddy from Usmania University, who will be talking to us about on fragmentation of long-lasting overdense meteor trail echoes detected with Gadanki MST radar. So, Mr. Reddy, you can start. Channa Reddy? You are not audible. And also, I think you need to go full screen. Your slides are visible on both sides. The side panel is visible on both sides. Vijayan, are you able to hear the audio?
Hello, sir.
Yes, I cannot hear actually.
Okay. Channa Reddy, if you can you confirm if you are able to hear us? You can just type yes in the chat box. So can LOC see if he's muted or?
Actually, she is unmuted. He's unmuted. So
Okay, so he's saying that he can hear us.
yeah.
So should we request logging out and coming back in, or?
Yeah, maybe that would help, or maybe there could be some problem with her microphone.
Yeah, try, if you are using a headphone, try unplugging the cable and putting it back. We still have, we can still use a minute to fix things. We'll just wait for another 30 seconds and see. I don't see the speaker in the list, so maybe we can. So Vijayan, if you can just type in the chat box that we will take Channa Reddy's presentation after Deepak Kumar Panda.
Okay. Okay.
Right?
Yeah.
So may I request Deepak Panda to share his screen and the LOC to give the permission?
Yeah.
Yeah, if you can. So we are moving to the, yeah. Just go to the first slide.
Yeah, it's
Okay.
visible.
Yeah, just a second. The next speaker is Dr. Deepak Kumar Panda from Physical Research Laboratory, and the title of the talk is Diversity in Mineralogy of Mukundpura Meteorite. So,
Good,
yeah, please go ahead.
good afternoon all, and thank you for giving an opportunity to present our work. So today I'll talk about the mineralogy, especially the diversity in mineralogy in Mukundpura meteorite. Just to give a brief, the mineralogical and isotopical studies of meteorite is very important to understand the early evolution of solar system and its history. So the sketch shows a early evolution of solar system where it shows that the early form solid CIA, AOA, and chondrules are basically the first form solid, and with time these CIA chondrules along with dust and gases accreted and form the big solar objects like planet and asteroid. So these meteorites are basically classified on the basis of their bulk composition as well textural texture, and chondrite is one of them, which is basically a primitive in nature, and they are very old, and that is was very important to study. These chondrite meteorites composed of basically the chondrule, matrix, and refractory inclusion. Um some of these chondrites are undergone through secondary processes like aqueous filtration, thermal metabolism, and shock metamorphism. So in chondritic meteorites also classified based on their mineralogical, petrological, and isotopic ratio to different types of chondrite. In these CI and CM type and CR type are the chondrite which has gone through the alteration process, and the water content in these type of chondrite the meteoroid has been classified that CI contains roughly around 20% and CM around 9% and CR 9%. Sorry, CR 9%. Depending on the diversity of the grade of alteration, there are the production of secondary mineral also varies in geometroid, and the production types of production of secondary mineral also depend on the type of fluid, amount of water, and the duration of interaction with the parent body. This just to show you that how the water content in the the secondary minerals is very important to understand. So this shows that the majority component of water is basically comes from your the secondary mineral called the phyllosilicates. So based on this, they also the people have classified what is the content of water and the classification of their meteorite. So depending on the grade of alteration, CM meteorite has been classified from 2.0 to 2.6, where 2.6 is the least altered. Pura is a CM2 type meteorite fall at Jaipur in Rajasthan 2017. And this is highly altered meteorite, and this is dominated by phyllosilicates and poorly characterized phase called the PCP. The other minerals present are carbonate, phosphates, FeNi metals, FeNi sulfur metals, chromides, and refractory minerals, mainly CIA, that is calcium aluminum inclusion, or the AOA, the ammoboid olivine aggregates. Tripathi et al. Has shown that the water content in the phyllosilicates in Mukundpura is roughly around 11%. This shows the mosaic DSC image of few chondrules, matrix, metals, and refractory inclusions. So I'll try to focus a few mineralogy from these coarse grains materials. So in Mukundpura, basically the controls are the ferrosilicate melt form the spherical objects called the control. And in Mukundpura, they almost all the control have been altered, and few are partially altered also has been observed. The size of these controls vary from 200 to 600 micron, but very few in large size controls have been altered. So one example, so in here in the left side is one control with a fine grain rim. So in almost all the rim, the control will find the surrounded by fine grain material, phyllosilicate material called the FGR basically. And in some material, we'll also see in that there is a extended rim, which is with divided as a inner and outer rim. Basically, inner rim are basically iron rich phyllosilicates, whereas the outer rim basically the Mg rich phyllosilicate. And the inner rim are coarse grain and outer rim are fine grain. Their formation still in debate. Some theory says that it's basically from the formed by the parent body alteration. Some says that it is a nebular in nature. So we are not going to debate on that. And this below shows the X-ray mapping of the same contour, which where the green color shows the Mg reach. So the center part shows the olivine reach, and the red basically are the iron map, and so the red color shows the iron reaches phases. Okay. So other type of meteorite, control we found in the Mukundpura are type 1A, which is basically the olivine frustrated in nature, and which is basically low in iron content. And then we also see type 1AB, where olivine along with pyroxene. So with these pyroxene are basically low calcium pyroxene along with metals. But here we can see that there is no rim around the control. So we have found both rimmed control surrounded by rim, as well as without rim. Also partially covered rim also we have found. So the other type of control we found are the barred olivine. So the light gray are basically the iron rich olivine, and the center dark gray are basically the mesostatic phase, and these mesostatic phase are basically altered to Mg rich phyllosilicates. Matrix are basically consist of fine grain materials of silicates, aggregates of silicates and metals and metal sulfide and organic compound. In Mukundpura, basically these matrix is basically dominated by phyllosilicate and PCP, and these are a few sections of the matrix. These are the classed, and these are some class. This is MG classed, and these are the poorly characterized phases PCP, and these are the phyllosilicate MG phyllosilicate. These are the iron rich phyllosilicate. This is again shown that PCP, and these are the iron rich phyllosilicates. These phyllosilicate, so in matrix generally we found both iron rich as well as Mg serpentine as and these phyllosilicate are low content aluminum, which varies from 2 to 5 weight%. The PCP are basically intergrowth of tectonite and concertite, basically known as TCI. It has found that in a higher grade of alteration, you will find the fibrous, large fibrous structure of PCP covered by the injuries phyllosilicate. So these structures we found large in numbers in almost all the sections, and these are few altered, means metal grain are completely altered, and the rim is basically the iron sulfide, and nearby you can see the rim also. This is a iron, pure iron metal, not completely altered, but inside you can see the altered phase and surrounded by rims, and these are basically Mg rich phyllosilicates. This is another PCP is nearby covered by the carbonate material. These are the carbonate phase. Our data, chemical data shows that the rim material is same as the matrix material. So this shows that the rim also the morphological features shows that these rims are basically say maybe from form in the parent body. All the phases, silicate as well as the altered phase have been plotted ternary in a ternary plot of iron, silicon plus aluminum as magnesium. So these shows the increase in gradation of your serpentine as well as this iron increase also shows the higher alteration. So the all types of silicate have been plotted. Yeah, these are all from the matrix. Similarly, this plot shows the all the main phases from the control. So this also shows that the mostly they are phyllosilicate rich. This shows that FeO content in Mg silicates varies from roughly around 15 to 20, 16 to 30%, and these are high sulfur content. We didn't find any mesostatic phase, so that shows that all the mesostatic phase has been altered in the earlier alteration phase. In the Fe-rich phyllosilicate, the iron content varies from 20 to 55 percentage. Large clump of PCP shows that the basically these are formed by the parent body aqueous alteration. In PCP, we found that the iron oxide to silicate ratio varies from 1.3 to 2.9 with an average value of 1.88, which basically actually we can categorize the grade of alteration depending on the FeO by SiO ratio. Also, the sulfur by silicates ratio also increases varies from 0.03 to 0.7. This also shows that with silicates content increase, that shows the higher with a higher alteration, the silicate in the fluid also increasing. The next is the carbonates and phosphates phase. So in alteration, carbonates are the also a minor component, roughly around 1 to 2% in volume percent, and this is one control. So these basically pink color shows the carbonate, and the rest are the phyllosilicates phase, and this is surrounded by also a rim. So this suggests that the calcium rich phase like a major glass or the calcium rich pyroxene may have altered to the carbonate. This is again a calcite, and this is surrounded by PCP and serpentine, and this also shows that the with higher alteration grade, the after the formation of carbonate, this is the formation of serpentine is form when the advancement of the aqueous alteration is there. This is one very few dolomite you find in Mukundpura. So presence of dolomite also shows the higher alteration grade, because in CI the highest almost all material has been altered, where you find the much dolomite as compared to the calcite. And this is one phosphate ring form around the phyllosilical clast. So these rim are roughly around 5 to 10 micron in diameter. So they are fine rim only, and nearby there is a formation of calcite. So this morphology of this phyllosilicate shows the flow of fluid also. So this formation of phosphate shows that this might have formed by the leaching of calcium from the CIA and phosphorus from the iron nickel phase. So this shows that we found very low amount of carbonates. Carbonates formed by the precipitation processes, and the our mineralogical and petrochemical study shows that there is different grade of generation of carbonates present in the Mukundpura mineral, and the occurrence of phosphorus shows that the phosphorus formed by the migration of phosphate and calcium from iron and calcium bearing Ci. Next come the iron nickel sulfate. So sulfide minerals very susceptible to alteration, and they are basically affected by the environment condition like fluid composition, temperature, oxygen fugacity, and pH. So the sulfides are basically formed by the precipitation or by the replacement of the primary mineral and from the troilite type of sulfide. So basic feature of this alteration in metal is basically the presence of pores. These are the small pores, and the reaction plants, then rim around the objects, and the intrusion also. You'll find sometimes this type of intrusion and replacement of primary minerals. So the other few metals where you can see these are the already altered and rims around them. These are the pores, and this here also in chondrule also we find that the metal has been totally altered, and this is also a iron nickel sulfide where you are saying can see the in between there is a fracture and fluid has been come inside and been altered. So the plot shows that we found mainly the parotide, triolide, pentalide, and then kamacite, and this is a This is only just a pit on a metal iron nickel metal, and the size of kamacite is large, that is 220 to 200 micron, and troilite are roughly less than 50. The other sulfides grain are roughly around 20 to 70 micron.
2 more minutes.
Hello.
2 more minutes.
Yeah. So we have found that the in kamacite type of mineral, the alteration zone are basically teclinite in nature, where the sulfide zone we are basically consodite, and so we can skip this thing. And we also found the magnetite formation. These are basically formed in the oxidation state. State. So iron is basically react with the water to form the magnetite. Then we have the refractory phase, basically the Ci and ammoid olivine. So these are very rare found. We are found only 2 to 3 only AOA. So these are basically phosphate rich and some high calcium pyroxene rich. As they are survived from the high temperature process like evaporation, condensation, so their study give more information about the nebular gas formation. So this is one we have seen. This is the phosphide. This is the calcium rich pages, and these are calcium low calcium pyroxene. These are spinel and one perovskite we have found. So this composition I am not going. So lastly, the Ci basically these are also very small grain in size, and mostly the spinel are found, and all the melalide has been altered, and very small inside the pyroxene grain has been also found. Well, this is one refractory mineral where we have found inside that a chromite, and these are the low calcium pyroxene are there. So in summary, we saw that the Mukundpura is a highly altered meteorite. Now all the chondrule have been partially or completely altered, Mesostatic phase have been completely altered to the phyllosilicates. Matrix is basically dominated by the phyllosilicates and PCP. Carbonates and in carbonates, basically the calcite are dominant, but a rare presence of dolomite also observed. And refractory mineral also rare. Secondary minerals are formed by the alteration of iron and nickel, nickel and tolite. And our mineralogical studies shows that Mukundpura alteration is not a single event but a multi-stage event. That's all.
Okay, thank you, Dr. Panda. So if anybody has questions, please use the chat box or raise your hand. We have a question for you from Shama Narendranath, and she's asking what is the significance of the PCPs?
Basically, if you see the PCP also shows that the condition of formation 1. The PCP basically stabilized at a formation degree of from 50 to 100, roughly 120 to 150 degree. People have done the experiment. So that shows the what is the temperature of your formation of the alteration situation, number 1. Number 2, that because it is a iron sulfide alteration, basically iron sulfide component. So this shows that they are formed in the reduction state. So this is also one environment shows that they are forming the this thing. Also in the classification of their alteration, the PCP are used, especially the iron to silicate ratio has been so used to find out the grade of alteration in the meteorite.
Okay. Okay. Thank you very much, Dr. Panda. We will now move to the next presentation by Chenna Reddy, and this is also the time for me to transition and hand over the controls to my co-chair, Dr. S. Vijayan. So Vijayan, if you can go ahead and take over the next set of talks.
Yeah, thanks, Vikram. Chenna Reddy, you can start your session. Please go ahead.
My presentation, my screen is visible.
Yeah, visible, and you're audible. Please go ahead.
Good, thank you. Thank you for the opportunity to present my work at NSSS 2022. I am presenting on fragmentation of long-lasting overdense meteor trail echoes detected with the Gadanki MST radar. This is the outline of my work. I'll just give a touch upon basic terminology, then Gadanki MST radar, the parameter chosen for this study, and some geometry of meteors, and the classification, head and trail. Then even in the trail echoes, we have underdense, overdense, and RST. But my focus is mostly on the last topic, that is long-lasting overdense trail echoes detected with the Gadanki MST radar. Just for the sake of completeness, I'll just give a brief on terminology associated with meteoroid, and meteoritis, and even fireball. So this is a meteoroid, and once it enters into the Earth atmosphere, it can be known as a meteor, and if it falls down, survives during its travel in the atmosphere and falls down on the surface of the Earth, it is known as a meteorite. And sometimes the entry size itself is very big, then it can lead to the fireball. So this is just give an overview on basic terminology associated with meteor, meteorite, and meteoritis that fall on the surface of the Earth. So of course, one more picturization, but my focus is meteorites are responsible for thousands of kilograms of annual mass flux into the Earth atmosphere, but its disintegration mechanism of these bodies is not known well, and hence their composition still remains a subject of debate in the meteor, particularly in the radar meteor community. Yeah, for this we use 53 megahertz Gadanki MST radar to study the meteor echoes, and the different classes of echoes have been presented, and we discuss case by case on the basis of their evolution. This is the picturization how the meteorite enter into the atmosphere, and where we have a vapor shield and impinging air which disintegrate the meteorite into the streak of light that we see in and time elapse shows the how it get disintegrate and dissipated. And of course this is in some sort of an simulation how time was a timeless simulation how meteor can get disintegrate uh, as it enter into the earth atmosphere. Yeah, yes. For the detection of meteors, we have two class of radars. One is a conventional VHF radars, and of course, in this category, all sky skymet will fall in this category. And other is high power large aperture radars like middle atmosphere radar of Japan, Marsi radar, Pansy radar, Ikamarka radar, such radars of multiple antennas that can give a single beam which is projecting to the some height, particularly in case of for meteor studies 80 to 120 kilometers or so. Yes, our Gadanki radar come under this category, but not exactly. It is in a high power large aperture radar. Though it has a frequency of 53 megahertz, not exactly fall in any of this category. As an aperture wise, it's a small aperture, but power is high power. So we can consider that Gadanki MST radar can be in between or another way intermediate to both the radars. That's a conventional VHF radar or high power large aperture radars. So this is an featurization of Gadanki radar and antenna array where frequency is 53 megahertz and which uses beam width is 3 degree. For the present study, the peak transmitter power is 2.5 megahertz and the number of antennas which are distributed in 32 by 32
Generally, LOC.
Yes, I cannot hear you, Chanardi.
Yeah, disconnected.
Is it audible?
Yes, we can hear you.
Yeah, sometimes in between it is going back. Yeah, the classification based on electron density, there are two categories, overdense and underdense. And this is if we receive the radar signal underdense, and this is an overdense. And in case of underdense, there is a sudden rise and slow decay of the signal power. Whereas in case of overdense, it's a gradual rise. It can be there for some times, and gradual decay will took place. Yeah. Based on geometry of orientation, the meteors can be classified into two categories. So one is down the beam, and the other one is transverse or specular meteor. If a meteor enter into the radar beam, particularly I'm talking about Gadanki MST radar are category of high power large aperture radars. So if the meteor enters like this, it will generate down the beam echo. If it is enter like this, it will produce an specular echo. In the case of specular, again, we have categorization the other way. The other categorization, depending upon the orientation, head echoes. If the echo is not yet completely falling in the beam, then such echoes are known as head echoes, and these head echoes are very much useful in calculating the radial velocities of meteorite. Other way, the speed of meteorite and other important parameter related to the meteor can be understood. Its astronomical parameters like eccentricity and others. Sometimes, but not always, Gadanki MST radar also detect the trial echoes where the meteor not get completely gives an eye, but sometimes at the end of the head echo, there may be flaring will take place because of the fragmentation of the meteorite. So as the meteorite survives, and at the terminal point, it may be get suddenly flares out. Such an echoes are known as terminal flare echoes. So these are the some of the terminal flare echoes. This is a single head echo with a terminal flaring, and most of the time this terminal flaring will occur at an lower altitude below the 90 kilometers of altitude, but sometimes it can happen even at a higher altitude. So this second example shows the multiple flaring. Some may be at an below the 90 kilometers of altitude, and some flaring even happens above the 90 kilometers of altitude. Of course, the other example shows the terminal flaring, particularly terminal flaring in the North 13 beam, where this is a sporadic E formation, and this is another sort of echo that's known as range spread trail echo. When Gadanki MST radar can detect underdense, overdense echoes as well as range spread trail echoes. In this example, I'm showing in this here I'm showing some of the overdense echoes detected with the Gadanki MST radar. High power radars mostly detect head echoes, but particularly Gadanki MST radar, which is an intermediate to both high power and conventional VHF radars, it is able to detect all categories of head echoes, all categories of echoes like head echoes and trail echoes like underdense and overdense. So in the overdense echoes can be detected mostly with conventional radars like SkyMet radar and all those things. But Gadanki MST radar can also detect overdense echoes. These are some of the examples. The x-axis shows the time period, and y-axis shows the height. And at the right side, I just plotted arbitrary unit, maybe the power or amplitude, whatever, at particular one or two range bins. So these kind of an ordnance echoes can be visible, can be detectable with the Gadanki MST radar in one or two range bins. So I plotted for this particular range bin, our height may be 88.8 kilometers. So it shows it is an overdense echoes where it is going in a oscillations, multiple oscillations. So within a few seconds of time, maybe 1 second or 1.5 seconds of time, it is showing multiple oscillations. In the next example, here it may be some head echo is appearing, but head echo is causing this overdense echoes where which goes multiple oscillations. Similarly, all other examples also shows the multiple oscillations in the power at that particular height. And yeah, my focus here is over-dense echoes. This is a classical example of over-dense echo where this it shows the range time intensity plot, and the left side shows the power and phase and unwrapped phase, where the x-axis is an time in seconds, and y-axis in case of power is an again arbitrary unit, and phase and unwrapped phase is an radian. So in this classical kind, it goes yeah. This can be explained with an Fresnel oscillations, where white and alternate white and black parts of the trail are formed, leading to the signal strengthening and weakening will takes place. That's an alternative constructive and destructive interferences will take place. Zones will take place, known as a Fresnel zones. So these can be explained with an Fresnel zones theory. That's where alternative constructive and destructive interference will take place. But the next case, what I am trying to show is it's on a completely different where the signal it's in a quite lot of difference in this. Oscillations are getting decreasing at some period of time, but whereas in this case, in the next case, oscillations are almost continuous, and they are not decreasing. Here, head echo, weak head echo, and which is causing this sort of long-lasting overdense echoes. So this long-lasting overdense echoes cannot be explained with classical ablation theory of meteor, but it can be explained with the help of fragmentation, where the head echo, the meteorite, which is causing a head echo, suddenly get disintegrated, and such an disintegrated maybe the more than two meteorite particles, they are giving the signal, and they are get interfere. And again, another such an example of long-lasting overdense echo. Why I'm showing again and again is that long-lasting overdense echoes can be detected at an all altitude, maybe the above the 90 kilometers of altitude, or near to the 90 kilometers of altitude, and even at a lower altitude also such echoes can be detected. That's why I'm showing another example that where the again long-lasting overdense echo can be detected at a lower altitude, as low as something around 82 or 83 kilometers of height. Yeah, that's long-lasting echoes can be detected in all heights. The number of such an echoes are relatively very less, maybe of 1 or 2% of the total echoes, but their disintegration mechanism is completely different from the classical ablation theory. Yes, another example where such an overdense, long-lasting overdense echo detected at a higher altitude, roughly around 118 kilometers or so. Yeah, such an echoes were also detected with an Arecibo radar of different frequencies. Arecibo radar of 430 megahertz were detected, but mostly at an slant. Such an echoes are mostly at an slant altitude. Yeah, but with an 43 megahertz,
2 minutes more.
which is also the similar to our Gadanki radar, also detected such an echoes. And this is a peculiar example. We are not sure about why such an echo were detected, because no other echoes can be visible, can be detectable at such a particular height, maybe of 80 to 120 kilometers. But this is a completely different peculiar echo. We are not sure about whether it is a meteor echo, or the echo may be something some other reason. Yeah, there were the fragmentation models which are helpful in explaining the process of a meteorite. This is the rubble and it can be get fractured as it is initial disruption will be something like this, and it can be get into the structures group, then it can be completely get separated, and as it gets separated, successive fragmentation because of the different uh, grains of different sizes will give signal. So fragmentation strength increases with the decreasing size of the grain. Yeah. Uh, yeah, I'm with this. I'm just giving the different signals or different echoes, meteor echoes detected with the Gadanki MST radar, and particularly this over long-lasting overdance echoes detected with the Gadanki radar. And these echoes cannot be explained with a simple classical ablation model, but we required fragmentation. Uh, Fragmentation of meteorite has to be considered to explain such an peculiar echoes. The fragmentation can be single fragmentation, or it may be a continuous fragmentation, or quasi-continuous fragmentation has to be considered for explaining such an long-lasting overdense echoes. Yes, with this. I'll just conclude my thing. Thank you.
Thanks, Reddy. There is a quick question by Dingra. What is the range? How far with up to which MST can detect meteoroids?
Yeah, with an frequency of 53 megahertz, Gadanki MST radar can detect 80 to 120 kilometers of height. As the frequency decreases, we can go for the lower altitude. Maybe of 35 megahertz, you can come to the 65 kilometers, as low as 65 kilometers to 110 kilometers.
Okay, there are a couple of questions by Dingra. You can please answer that in chat. Thanks.
Okay.
Thanks for the question. Yeah. So now the next speaker is Megla from ISRO.
Dr. Vijayan, I'm sharing my screen.
Yeah, just a moment. Reddy, can you? Yeah, now you can share.
Is it visible?
Yeah, it's visible. Please go ahead, Megla.
Good evening. I'll be presenting on a mission which is in the study phase and aim to do in situ exploration of lunar polar regions. The poles of the moon are the coldest places in the solar system, and we all know that water ice does exist in the lunar poles. In the polar regions, there are large areas called the permanently shadowed regions, which has cold traps or which act as a reservoirs for holding the volatiles and water ice stable for billions of years. Water ice measurements are carried out using a variety of techniques such as the radar-based measurements, UV-vis, NIR spectroscopy, laser-based studies, and also by neutron spectroscopy. Multiple observations in the lunar surface shows the presence of water ice. For example, an impact experiment on the KBS crater of the South Pole by the L-Cross mission unambiguously detected water in the ejected plumes. These plumes also contained other volatiles such as hydrogen sulfide, NH3, sulfur dioxide, carbon dioxide. So this is the kind of a measurement which has done the direct detection without any ambiguity. In addition, in the LRO orbiter, the Lyman Alpha Mapping Project LAMP and also the laser-based laser altimeter had measurements over the South Pole permanently shadowed regions, and those studies shown that surface reflectance properties, which is consistent with the presence of water frost, and the weight percentage is around 0.1 to 10 percentage. In addition to uh, LRO and LCROSS, the Moon Mineralogy Mapper on Chandrayaan 1 detected the around 30 weight percentage of water ice mixed with the regolith, and this is detected over mainly over the polar regions, that too in the first few of the lunar surface. In the same Chandrayaan 1 mission, we had a MINISAR experiment, which is a S-band radar, which has detected subsurface water ice, and there was one payload in the Moon Impact Probe, which is a mass spectrometer, and it has detected enhancement of water molecules when when the uh, impactor crashed onto the lunar poles. Currently, in the Chandrayaan 2 mission, there is an imaging IR spectrometer payload IARS, which has unambiguously detected the hydration absorption features around 3 micrometer. This is a payload which can go up to 5 micron, and this detection was done in all latitudes and in surface types. So there is no confusion that about water. The water is present in the lunar polar regions. Shown here is the mosaic of both North and South Pole region and also its topographic map. In the recent Williams et al. Paper in 2019, it quantified that approximately 4.5 percentage of the South Pole and around 1.8 percentage in the North Pole has PSR regions, and whose temperature is less than 110 K. It can go up to 110 K or less. In addition to PSR, there are some seasonally shadowed regions which acquires cold during the lunar winter, and this also adds to the PSR, and the percentage of PSR may go up to 12.8 in the South Pole and 7.9 in the North Pole. In summary, there is definitive evidences that PSRs in the South Polar and North Polar region host water ice and also water volatiles for billions of years. But the quantity of water, that is, the amount of water existing over the poles, the quality of water, whether it exists in the form of H2O or it is mixed with other volatiles, what is the state of water, like whether it is in the form of frost or in a liquid or nicely mixed with a regolith, what is their distribution, is there any time variation, and how to access lunar water, these are the questions still remain unanswered. Recently, we have seen a renewed global interest on the moon, mainly because almost all the agencies, if you name, all are aiming to go to moon for the polar exploration. Because moon is not just for science, it also has some technological and economic benefits. After NASA and ISRO discovered water on the polar regions, there were a lot more things which came up, like whether this water is drinkable, whether O2 has can be dissociated and it can be used for a breathable air, or whether H can be used as a rocket fuel in the form of fuel cell technology. And moon, because of its proximity to earth, this could be used as a test bed for demonstrating certain technologies for future deep space exploration, especially when we talk about moon to Mars scenario. And this low gravity environment of the moon can also be explored as a rocket platform, mainly when you want to have a sustained presence of human presence in the solar system. So, moon has both scientific and also exploration or resource benefits. In this graph shown here is the resurgence of interest in this decade from 2020 to 2030, wherein you could see missions from China, the Chang'e series, and Luna series from Russia, Chandrayaan 3 from India, and slim kind of missions from Japan. All are going to the polar regions. There comes the Artemis ambitious plan from NASA to send the first woman and the next man to the moon, and it also has Viper kind of rovers to explore the polar regions, such as the Noble Crater in the South Polar region, and a number of CLIPS missions wherein the commercial people are also pitching in to make their own lander and rover go to the moon and explore the polar regions. In addition to exploring for human presence, China and Russia are going with the plan of International Lunar Research Station on the Moon, which is a permanent research station for doing astronomy and also lunar science. So, when you name a nation, I mean, name a space agency, everybody is now going to moon, and mostly all are going with the uh, bilateral and multilateral cooperation. For example, Artemis, which has the collaboration of ESA, Canada, and so many other countries. In the same context, ISRO and JAXA are now together. It is actually a bilateral cooperation to explore the lunar polar region. When we look at the um, Indian Lunar Exploration Program, it is basically driven by science, and we believe in going as logical next steps. Chandrayaan 1 in 2008 was an orbiter and an impact probe, and this is a mission which has the credit of discovering water on the surface, subsurface, exosphere, and also water which could be of endogenic origin. Beyond Chandrayaan 1, now we have Chandrayaan 2 orbiter with lander and rover configuration. Though our lander and rover was not successful, our orbiter, because of our excellent mission management and the robustness of Mark 3, we will be around the moon at least for 7 years. Right now, 2 years of observations are completed and we are in the third year. To demonstrate the landing and roving, we have Chandrayaan 3, which will be launched this year, 2022. It has a lander and rover configuration. Then now what we are going to talk about is a mission which is beyond Chandrayaan 3, which is tentatively called the Lunar Polar Exploration Mission or the LUPEX mission. And the LUPEX mission is will be having a lander, a rover to do in situ analysis in the South Polar region. As I said earlier, it is a bilateral cooperation with Japanese Space Agency, and we are aiming to go in 25 time frame. One step beyond LUPEX, our lunar science community is very much interested to go for a sample return mission. This is in a very preliminary study phase and which will be discussed later. When we see the mission concept or the mission LUPEX as a whole, as I said earlier, it is a South Polar landing mission. South Pole, in the sense 85 to 90, is what is targeted, and it's a mission to study the water ice and also volatiles. When you look at the responsibilities, the lander portion will be done by ISRO. That is, ISRO holds a major responsibility in the design and development of the lander, and landing is also ISRO's responsibility. And rover is from JAXA, and the lander and rover will be interfaced and um, launched from Japan using a JAXA launcher. And this mission, as you see in the pictorial representation, there will be a lander, and then the lander will leave out the 350 kg rover. It's a quite very big rover, and this rover hosts the payloads both from the Indian side and from the Japan side. Um, this mission, the science objectives are to characterize the volatiles and its composition in the lunar polar region. When you see the science objective as a whole, it is like water and other volatiles. When we split down the science objectives, it is like focusing on the quantity and quality of water in the perspective of whether it can be used for future exploration activities, that is utility point of view, and the lunar water accumulation mechanism in order to estimate what are all the water rich sites in the lunar polar regions, and then to study in the landing site what are all the volatiles and elements or if possible organics present on the polar region, and to understand the properties of volatiles. The set of payloads to study the science objectives are selected both by India and Japan. Both the list of payloads which I am going to present now are only tentative, and these list will be finalized during the next phase of the study. Right now, we are in the phase A study, which started in 2020, and we are planning to complete it by March of this year, and then phase B will be starting. From the Indian payload side, we have a ground penetrating radar which is working in 50 and 500 megahertz, and the objective of GPR is to do radar observation up to 1.5 meter to look at the subsurface features and also the presence of water. There is an NIR spectrometer to detect the water ice signature and also mineralogy on the lunar surface. There is a plan uh, to include a thermal probe to understand the dielectric constant and the geophysical properties, which we could say that as an indirect detection of whether water ice is present in that region. And there is a Raman spectrometer, which is actually a will be actually seeing the sample for detecting the minerals and also organics if it is present in the lunar samples. This set of payloads are selected by the Apex Science Board, and these are still in a tentative list which will be finalized in the next phase. From the Japanese side, there is a set of payload. There is a neutron spectrometer to do the observation during the rover transfers, and there is an NIR spectrometer too, similar to the range is different, but it's similar to our Indian side for the hydroxyl and water observation. And there is a package which uses the drilled samples. Uh, I have to mention that in this mission, when there is a rover transfers, there is a drill, and the drill will make a borehole and take out the samples, which will be given to both Indian and Japanese payloads for analysis. So this drill will be taking out the samples every 25 centimeter till the depth of 1.5 meters, and JAXA will be measuring the samples for the water content, and also it will heat the sample and study the volatiles and species from the heated vapor. And there is an mass spectrometer in the rover too. The concept of the mission is quite very interesting, that the rover, the lander, will be landing in a permanently sunlit region within the range of some 100 meter, and then the rover will come out of the lander, and the rover will move over the site which is around the exploration area will be around 1 kilometer square. In this 1 kilometer square, there will be points which will be of permanently shadowed region, and also points which are permanently sunlit. The rover will traverse over the path and do the observation, and in the completion of 1 kilometer square area, it is called as one observation. So, in the similarly, we are planning to do around 3 to 6 observation using the rover. As I
2 minutes
said,
more.
okay. As I said earlier, the polar region we are going to land within 100 meters square at around 89 degree, and 1 kilometer exploration area will be studied. And in the importance of this mission is that there is a possibility that the rover may go inside a PSR and we can do observations. It could be a direct exploration of a permanently shadowed region. When a drill is drilling the samples, it scoops out, and then it is a kind of laboratory. The rover is a kind of laboratory which is sitting on the polar region, and the mission life is expected to be around 6 months. The criteria which we used for selecting the landing site is 89 to 90 degrees south is what is targeted, and the landing site should have an illumination of greater than 60 percentage, and at least 100 days of continuous illumination should be there. And the site should be it should be able to communicate to the earth, and the site should have a uniformity like less than 10 degrees slope is accepted, and proximity of PSR is an added advantage. The operational scenario of payload is when we when the rover traverses, the GPR, neutron spectrometer, and NIR will do a coarse mapping of the water ice presence. And after that, once the water ice presence is detected, the rover will stop and start drilling. Once the drilling it comes out, and the sample will be distributed to the Japanese instrument where they will measure it for water and then heating it for the volatiles, and then one scoop will be given to the Indian payload to study the mineral presence and also the organics. This is an operation which we have finalized in the phase A report. Since we are in the study phase, the rover and lander configuration, design and development cannot be explained. So thank you so much.
Thanks, Megla. There's a question by Koina Das. Uh, Chandrayaan 3, 5, and Lupex all will land in South Pole region. And if so, what is the difference in their objective?
Chang'e 5.
Chandrayaan 3,
Yeah.
5, and Lupex.
Chandrayaan 3 will not be landing in the exactly in the polar region. It is a near polar region which is around 70 degrees south. So it is far from the Lupex which is around 89 degree. So Lupex is the one which is going to land exactly in the polar region. Chandrayaan 3 is the near polar region around 70 degrees. So we can see the enhancement of hydrogen, but about water, we are not sure.
Okay, Dingra has a question. How are the rovers going to be powered? Regular solar panels or RTGs?
Yes, sir. It has a solar. We don't have an RTG or RHU in this mission. It is a solar panel, and it is planned in such a way that we have a good battery with us, and the solar panel is a rotatable mast kind of thing. Um, it is like we will go, and when there is a permanently sunlit region, it will be powered fully, and then we will start exploring the permanently shadowed region. Then we will come back to the sunlit area for powering it.
Okay, thanks, Megla. There is one more question you can answer in the chat.
Yes.
Okay, now we'll go to the flash talks by
Thank you.
students, and I'll request Mosam Mehdi from President University to share the screen. Megla, you can stop sharing your screen. Yeah, Mosam Mehdi from President.
Yes.
Yeah. So stick to 3 minutes.
Yes.
Yeah, screen is
My screen is visible, right?
Yeah, please go ahead.
Okay. Hello, everyone. This is Mosam from Presidency University, Kolkata. My research is about studying the properties of the extrasolar planet atmospheres. We mainly focused on the atmospheres of hot Jupiters using the concept of transmission spectroscopy. Now, we know that as the planet transits, its atmosphere is illuminated, and the transmitted light through its atmosphere, it can be observed, and it can be analyzed for understanding the absorption spectra of different chemical species that may be present in the exoplanetary atmosphere. Now, we actually see a light curve, and taking consideration with the transmission part, the transit part, we can plot a transit depth versus wavelength spectra and can use it to identify different chemical species that may be present. Now, for this, we are using a software, Platon, which is quite new. It is actually a Python package that calculates transmission and well as emission spectra for exoplanets. And it can also retrieve atmospheric characteristics based on the observed spectra. So actually, we did a study on various exoplanetary and atmospheric parameters on the transit depth, like the influence of mass of the planet, radius of the star, radius of the planet, temperature, carbon dioxide ratio, metallicity. But we mainly focused on temperature and using the custom abundances available with Titan. We changed the abundance of a particular chemical species and replotted it with the original spectrum, and using these in our work, we have found significant detectability of around 18 chemical species. Now, in the next part of our work, we did atmospheric and planetary parameters retrieval from spectral observations of hot Jupiters. So we retrieved the parameters for two hot Jupiters, HD209458b and XO1b. Now for retrieval, we are using the processed results for transmission spectra that was obtained by Deming et al. In 2013. Now the retrieved results and means our retrieved results and uncertainties are consistent with the based values that are available in current literatures. Thank you everyone for listening. Thank you.
Do anyone have a quick question?
Yes.
Any questions? Okay. If it is not there, I invite next speaker, Koina Das. And please share your screen. Das. Yeah, go ahead. Koina, you can go ahead. Hello. Koina, you are not audible. Koina? Dinga, can you able to hear? LOC?
Yes, Koina is actually inaudible. She is unmuted.
Das? Can hear us? Please type in chat also.
Okay.
Yeah,
should
now we
I
can hear.
share my screen? I'm Dr. Gurpreet. I'm the next party.
Okay. We have to remove. Koina, can you remove your screen sharing so we can take it your presentation at last? So I invite next speaker, Vigneshwaran. Vigneshwaran? Yeah.
Is it visible, sir?
Yeah, go to full screen and start.
Good evening to all. Today my presentation about chemical weathering and lateration of Savangi formation. It is a potential Martian oxide. In this study, international environment conditions from rocks. Savangi formation is located in Tamil Nadu. In this geological map refers the Savangi formation stratigraphy. In this stratigraphy, the base state of stratigraphy is basal conglomerate. It is formed by the deposit, which is formed by the fluvial activity. The clays are mostly allanite rich and also smectite are associated with it. Later, the marine transcription regression of activity formed this marine sandstone limestone. After this side formed the region, it formed it is feels the wet and dry conditions. These wet and dry conditions is a favorable condition to form a laterite throughout the India. The major laterite occurrence throughout the India is Deccan Trops and also Kerala region, Goa region, and South Tamil Nadu regions. But the parent rockets differ from all the sites. A Sivangate formation is potential site because it have a fluvial parent rock. So the lateration may be occurred in the Mars. So we are interpret the Perseverance rover images and Curiosity rover images. In this image, we can see the rock weathered to form a spherules and clay soil in it. It is one of in situ alteration, in situ weathering. It is formed by the fluvial chemical weathering. Later, it weathered to form a spherules and clay kind of things. In Sivangate formation, also same like this. It is after the laterite formation. It weathered by the recent climatic condition to form a spherules and also clays, kaolinite-rich soil in the surface. Later, the humidity and wind activity also affect this laterite to form a MnO-rich, manganese oxide-rich surface coating. These material, this kind of process is very similar to the Martian conditions. So we express the Mars maybe have a in paleo conditions. It have a episodic wet and dry conditions. The surface may be rich in kaolinites. The kaolinite formed from these laterites and also iron oxide assemblage just and in the spherulitic nature. The surface coating of MnO is very similar to our analog site. Thank you.
Yeah, any questions for Vicky sir? Okay, so I invite next speaker, Gurpreet Kaur. Please go to full screen mode and go to full screen. Full screen.
Very good. So, am I audible?
Go ahead.
Very good evening to all. My name is Dr. Gurpreet. In this work, today's talk, I will discuss about my recent work. Earth is known to have formed by gravitational accumulation between planetary embryos in the giant impact stage. The collision of proto-Earth with a planetary embryo, typically the size of Mars, could have created the Earth-Moon system. Previous study they show that Earth formed by accumulation of ancestral type material, which is of reduced type. Apart from this, study they have shown that Earth formed very late during a time scale of around 10 to 11 million years of solar system. However, the recent studies they have shown that Earth formed very rapidly during the initial 5 million years of the formation of solar system. Apart from this, recent studies they have shown that ancestral chondrites they are not volatile free, they are volatile rich. They contain around 0.1 to 0.54 weight% of water. So it means that if a impact generator steam atmosphere at the surface of Earth during accretion, the blanketing effect of this atmosphere could have melted the surface of Earth to form magma ocean at the surface. So in this work, what we have done, we have studied the differentiation of Earth's during and impact generators atmosphere. So the interior of Earth was heated due to heat of 26 aluminum, and the surface was heated due to the blanketing effect of impact generator steam atmosphere. So you can see here that in this result, which I'm showing here, Earth is this result is for 0.4 Earth mass embryo. The interior is heated due to the short-lived radionuclide 26 aluminum. You can see here that this is a temperature due to the efficient 26 aluminum, the surface temperature has increased to around 25 to 2800 Kelvin, which resulted in the melting of interior of Earth, and the surface was heated due to blanketing effect of impact generator steam atmosphere, due to which the surface temperature has increased around 3500 Kelvin, which resulted in the formation of magma ocean at the surface. So you can see here that here there is this thing shows the core formation inside the growing Earth. This thing shows the formation of magma ocean at the surface due to blackening effect, and here you can see here the formation of iron core at the center due to the efficient heating by 26 aluminum. And you can see here that a complete core formation around 3.9 million year inside the 0.4 Earth mass embryo due to these two heat sources. The results of these studies are good in good agreement with the results of recent studies for the early accretion and differentiation of initial phase of Earth during the initial 5 million years of the formation of solar system. And this is perhaps the first model which have incorporated the effect of impact generator steam atmosphere and considered the ancestite chondrites to be volatile rich. Thank you.
Thank you, Gopal. And may we call Anish Kumar. Anish?
Sir, am I audible?
Yeah, so better to the screen. Yeah, please share your screen. You're audible. Your screen is not. Yeah, it's visible. Go to full screen mode and. Yeah, go ahead, please.
Okay. A very good evening to one and all. Myself, Anish Kumar. I am a research scholar from Department of Geology, University of Kerala, Trivandrum. My topic is impact-induced deformation features from Ramgarh Impact Crater, Rajasthan, India. Ramgarh Crater is one of the confirmed impact crater, complex impact crater with a diameter of 10 km and a collar elevation of 250 meter. Lithologically, the crater is composed of Neoproterozoic Mandar, a group of sediments in which sandstones, limestone shales, and some patches of quartzites are exposed in the area. The Reva sandstone, which is exposed as patches in the center of the crater, which preserves some shock-induced deformation features within it. And here, this is the geological map of the area. We have collected samples for both petrographic and geochemical studies. And petrographic studies, we have calculated the CA with the chemical index of alteration values. And CA values of almost all the litho units having very high values of quartzites having more than 80%, sandstones and shales having more than 75% CA. And which shows that they have undergone, the major litho units have undergone very high intense chemical alteration. And this might have removed majority of the shock features from the major litho units of the study area, and which is only limited, the shock features are only limited to the river sandstone. This figure shows highly intensity fractured sandstone in the study area. And coming to petrography, we have observed planar fractures, planar deformation features, brecciation and melting, this type of features, and formation of diaplectic glasses in quartz grains. And these are the micro thin sections, micro photographs, which shows the shock features. Based on this, we have prepared a Hugh curve, and in which we propose the pressure of shock. The shock pressure is more than 25 GPa with a corresponding temperature of less than 1000 degrees centigrade. And we have plotted some bivarious plots and sandstone classification diagrams, provenance classification diagrams and all. And we can see that the sandstones in the study area comes under quaternary to sublithoranite type. And in tectonic settings, it comes under passive margin type, and in the provenance, it comes under felsic igneous province. It has came from felsic igneous province. And we have the geochemical data, some of the major traces and RE values are tabled here. And from this, we can see that all the values are in ppm. The chromium, cobalt, and nickel values shows very high values in the which is rather uncommon in the normal background values of the sandstone in the study area. And we have plotted the geochemical diagram. We can see that the contact normalized RE pattern and primitive mantle normalized RE patterns that we have drawn. And in contact normalized RE pattern, which shows LRE enrichment and europium depletion. And in primitive mantle normalized RE pattern, which shows enrichment of lead and europium depletion. We can also see in this figure that the very high values of chromium and nickel, scandium in some of the samples, and copper enrichment in almost all the samples. And from this petrographic and geochemical studies, we can say that the rambler structure is, there are evidences of impact shock-induced deformation structures from rambler crater. Thank you. Thank you, sir.
Yeah, thanks, Anish. And I'll call the final speaker, Koina Das.
Hi, can you hear me?
Yeah, let please share the screen. Yeah, go to.
Okay.
Anish, can you unshare your screen?
Just a minute.
Yeah.
Can you see my screen?
Yeah, go to full screen mode.
Yeah. Okay.
Yeah, please.
A very good evening to everyone present. My name is Koina Das and I'm currently doing a PhD at Latmos, France. The topic of my presentation is seasonal variation in the composition of Martian upper atmosphere. The data for this research has been taken from the MAVEN neutral gas and iron mass spectrometer. Mars has a similar seasonal pattern like our planet, but there is a huge temperature variation between the seasons in different hemispheres. For in the northern hemisphere, it has mildly warm summer and mildly cold winter, whereas southern hemisphere has extreme winter and summer conditions. The plot over here shows the variation of CO2 density in Martian year 33 at a height of 170 kilometers from surface. The reason we chose CO2 gas for our study is because it is non-reactive and hence studying its density pattern would show us how the upper atmosphere reacts to different changes. Density decreases when the atmospheric temperature becomes less than the frost point of CO2. Hence, density decreases the most when the planet is farthest away from the sun during the spring and the summer season, and least when the planet is closest to the sun during the autumn and the winter season. In order to understand the seasonal distribution of CO2, we have taken data for 3 consecutive Martian years. The image over here shows the position of Mars with respect to Sun throughout a year. For each season, I have plotted the CO2 density distribution over the entire planet at a fixed altitude of 170 kilometers. As mentioned earlier, there is a variation in thermospheric density depending on the amount of sunlight falling on the planet in each season. Hence, change in solar insolation affects the density pattern. Second process that affects the thermosphere are the dust storms, which are created by large pressure differences between the two hemispheres. They increase the upper atmospheric CO2 density and are more frequent during the autumn and the winter season, which is another reason why we see more density during these two seasons. Third process are the different atmospheric circulation patterns taking in different seasons. In the spring and autumn season, hot air rises from the equator and moves towards the pole, thus increasing the density near the poles. In contrast, in the summer and the winter season, hot air rises from one hemisphere and moves towards the other hemisphere, thus increasing the density there. Apart from these seasonal factors, certain local factors like gravity waves, atmospheric tides affect the thermosphere as well, but their study is not in the scope of my work. An unexpected warming was observed in the northern polar region during the winter season and in the southern polar region during the summer season. And this polar warming is caused due to various factors like dust storms, gravity waves, atmospheric circulation, and so on. Comparing the CO2 densities between these two polar warming regions showed us that the winter polar warming is more than the summer polar warming because of high solar insolation and dust storms in this season. Currently, I am researching on the effect of gravity wave on the southern polar warming in the summer season. Hope you enjoyed the presentation. Thank you very much. Please feel free to contact me in my mail address mentioned here.
Thank you. And now over to session chair, Dingra.
Yeah, thank you, Vijayan. Thank you all the speakers and the audience for interactions. And I see a message from the LOC. The MS Teams link for the closing ceremony tomorrow can be found in the web information kit shared with you in a previous email. So please join the ceremony tomorrow using that link. That's all from my side. Back to LOC.
Thank you, Professor Dingra. Thank you, Sir Vijayan, sir. So with this, we come to the end of talks on solar and planetary sciences plenary session. So thank you all.